Okay, for exponential functions, we have f of x equals a times b raised to the x. So this b represents the base, it's going to be a number. A could be a number as well. And the x is going to be our exponent. So our input value is our exponent. Some special properties of these exponential functions is that a cannot be 0, because if a is 0, we have a constant function, y equals 0. Also, b cannot be equal to 1, because if I have b raised to the x power, it's also going to be a constant function, because 1 squared is 1. 1 to the third power is 1. 1 to the fourth power is 1, and so on. So also b has to be positive. So I'm not allowed to have my base be negative, because if I square a negative, it becomes positive. Cubing a negative, we get a negative. To the fourth power, we get a positive. So our graph would end up being switching back and forth between negative and positive, which is no longer an exponential. So here are some examples of what an exponential looks like. And these are examples of what an exponential does not look like. Let's move on to looking at graphs. Now, in order to get the information about the domain, the range, the intercept, the asymptote, the end behavior, and where this function is increasing or decreasing, you have to actually be able to graph it first. So in order to graph it, I need to plug some values into x and get y's. So on my calculator here, I'm going to go ahead and go to my y equals, and I'm going to type my equation, y equals 3 raised to the x. Then I'm going to hit second, graph, and this takes me to my table. So you can see at -4, we have 0.012, so it's 0.01. We're rounding 2 decimal places. At -2, 0.111, -1, 0 is 1, 2 is 9. And the reason is because we're taking these x values and saying 3 to the -4th power, 3 to the -2, 3 to the first, 3 to the 0, 3 squared, 3 to the 4th power, and 3 to the 6th power. The next thing we're going to do is we're going to plot these points on our graph. So I'm going to go ahead and graph the right side of this graph because it's easier, nice whole numbers. I have 0, 1 is my first point. 2 and then 9. 1, 2, 3, 4, 5, 6, 7, 8, 9. 4, 81, all the way up here. I draw in my graph. And you might be asking, how did I know how this tail was going to behave? If we look at our table here, as my x is getting smaller and smaller, my y values are getting incredibly small, very close to 0. But if you keep going, you see that it never actually gets to be 0. It gets smaller and smaller and smaller and smaller. So for that reason, this graph approaches 0. So that means that our asymptote is at y equals 0. Next, the range. Look at my y values. I have no y values on the bottom of the graph. So that means my graph only exists in my positive y's. Now I do have this asymptote, so it goes from 0 to positive infinity. 0 because it doesn't ever touch 0, so it's a parenthesis. Domain. When we plug in x values, you notice it doesn't matter what x value I plug in, I'm always going to get some kind of answer. Because there's no errors, it means my x values are all real numbers. In interval notation, we write -infinity to positive infinity. Go to the graph. Y-intercept. Where does this graph touch the y-axis? Right here at the point 0, 1. So this means my y-intercept is the point 0, 1 or just 1. End behavior. We have two types of end behavior. Left end behavior and right end behavior. The left side of our graph is as x goes to negative infinity, because the left side, if you think about it, it's going negatively forever. The right side of my graph is x goes to positive infinity. Again, same thing like we said for negative, except we're going in the positive direction. So when I write my limit, I'm going to write the limit as x approaches positive infinity of f of x. So this is saying on the right side of my graph, what is my y value doing? So starting at 0, looking at the right side of my graph, my y values are going up, 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 up forever, which means positive infinity. On the left side, limit as x approaches negative infinity, my graph gets closer and closer and closer and closer, but never touches 0. So that limit is 0 because it gets very close, but it never crosses. Last thing, increasing. This is asking what interval is this graph increasing? The way we read it for increasing, decreasing, and constant is from left to right, just like you would read a book. So, from the left to the right, imagine yourself walking, and walking. Are you going to be going up a hill or down a hill? Since I'm walking up, this means that I am increasing. There's nowhere where my graph is decreasing. So we are increasing everywhere, which is negative infinity to positive infinity.